Welcome back. So I have a block here and it experiences the force of gravity that points down. And so this block is held in place by these two cables. And so of course, this force of gravity that you have here, its magnitude is equal to the force that you have here. However, we are interested in this force here and this force here. Let's say that this point here is A, this one is B, and this one is C. Let's say that the distance from here up until here is d meters, which means that this one is d over 2 and this one is d over 2. So you can see that you have symmetry here. So the length of this cable is L, and on this side the cable has the same length, L. And that also means that here and here you have the same angles. Let's call them alpha. Then let's call this height h. Then this force here, it's FBA, and this one is FCA. And from symmetry you already know that they are equal forces because you have the same alphas here, and you have d over 2 here and here. And now in this exercise, you don't have to calculate anything specifically. In this exercise, I challenge you to mathematically prove that as this length goes up, this force and also this force that we can just call F because they're equal, that it goes down. We had a problem where you saw it conceptually, but now I challenge you to mathematically prove it. As a hint, I recommend you to use equilibrium principles, and in order to prove that as your length increases, your forces in those cables go down, for that, use limits. So essentially, you have limit as L goes to infinity, and then you will have something here, and then you get something, and from that, you will mathematically prove that as your L increases, your F decreases. So try it out by yourself, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now mathematically prove that as your L increases, your F decreases. I'm only gonna apply the equilibrium principle in the y direction. So I'm gonna write FBA times sine alpha plus FCA times sine alpha minus W equals 0. It makes sense, right? If I create this boundary and you have W here, then since this block is not accelerating anywhere, it has to be held in place by the y components of these two forces, and I obtain them here. However, remember that both of them are F, so I have 2 times F times sine alpha, and then this one will go to the other side, so it will be like this. That means that F equals W over 2 times sine alpha. So this is my result. Now right now, we have a force as a function of alpha, but we need force as a function of L. But here you can see that you can express this sine alpha like this. Sine alpha equals h over L. That means that this formula here, it can be written like this. F equals W over 2 times h over L, or simply W over 2 times L over h. However, right now, it's not obvious that longer cables mean less force. And that's because if L increases, then h also increases. However, what we have here is 2 right triangles. One is here and the other one is here. So I can use a Pythagoras theorem where I say that L squared equals h squared plus d over 2 squared. And that can be rewritten like this. H squared equals L squared minus d over 2 squared. That means that h equals square root and then L squared minus, and then I have d squared over 4. And now I will replace this h with this expression here. So now force equals W over 2 times L over, and then instead of h I have this expression, square root of all this. The good thing now is that this d squared, it's constant because the d value does not change when your L increases. H did increase, but d does not increase. Now right now, if you look at this part here, so this one, is it less than 1 or greater than 1? Well, let's see. If you have some kind of number for your L, then here in the denominator, you square that number, but then you subtract something from that number, and then you square root it. So let's say if you did not have this one here, then you would have L over square root of L squared, which would be L over L, and it would be 1. However, here you subtract something from L squared, which means that this number here will be smaller than L squared, which also means that if you square root it, then this number will be less than L. Remember, this one would be L, because you have square root of L squared. But this number here, if you square root it, it will be smaller than your L. If it's smaller than your L, that means that you have a bigger number here, and you have a smaller number here, which means that this needs to be greater than 1. Which means that in this equation, your force, it equals W over 2 times something that is greater than 1. So as a result, your F will be greater than W over 2 for sure, because you're multiplying W over 2 by a number that is greater than 1. But now what I will do, I will take the limit of this function. So I will write limit as L goes to infinity, meaning as L increases. So I have this function here, and now I need to find this limit. So what I will do on the side, I'll take this portion of the equation and I will reorganize it like this. I have L in the numerator, but then in my square root, I factor out L squared. So I will have here 1 minus, and then d squared here over 4 times L squared, like this. And so I can rewrite this equation like this. L over square root of L squared here, and then square root of this one. So this here, it becomes L, and so I can cancel them out, and so I'm left with this expression here. And so now I'm gonna take this expression and I'm gonna put it here instead of this one here. And so I will write limit as L goes to infinity, W over 2, and then here I will have 1 over square root of 1 minus d squared over 4 times L squared. And so as L goes to infinity, this L here becomes bigger and bigger, but it's in the denominator in this expression, which means that as L approaches infinity, this term approaches 0. And if that's the case, then this entire denominator here, it approaches 1. because you have something that is 1 minus a term that is approaching 0. And so underneath this square root, you would have 1 minus and then the term that approaches 0. So under the square root, everything would approach 1. And if you take the square root of something that approaches 1, then that also approaches 1. That's why this entire denominator approaches 1. And now here, you have 1 over something that approaches 1, which means that this entire ratio approaches 1 as L approaches infinity. And now remember, this ratio was greater than 1. So you multiplied W over 2 by something that was greater than 1. So your force was definitely greater than W over 2. But now, as your L approaches infinity, you will multiply W over 2 by something that approaches 1, which means as L approaches infinity, F approaches W over 2, because this ratio here would become 1, and W over 2 times 1 would give you W over 2. And that's how you mathematically prove that as L goes to infinity, as L increases, your force decreases. When your L has some kind of value, let's say a random number, meters, then your F is greater than W over 2. But the greater your L becomes, the closer you get to W over 2, which means that your force would decrease. And it makes sense because if this is your block here, and this is your force of gravity, and your L approaches infinity, then as your L increases, and increases, and increases, then as your L approaches infinity, then it would look like this. We use this notation in order to denote that something goes to infinity, because of course in reality your length cannot be infinity, but as an idea, if something goes to infinity and it never ends, then we just draw an arrow here and here as well. And note that this is not a vector arrow. This is just to denote that the lengths of your wires approach infinity. And if that's the case, then you have 90 degrees here, 90 degrees here, and since you have symmetry here, d over 2, and here as well d over 2, then if this is your force of gravity, then in this configuration, it's normal that it is balanced by these two forces which are equal to each other, because you have symmetry here, and it means that this one is W over 2 and this one is W over 2. Together, they will give you a force vector that has the same magnitude like this W vector, but it's in the opposite direction. And so now you mathematically see that as your L goes to infinity, you approach this situation where your wires are perpendicular to the block, and so in terms of forces, you approach the situation where on one side you have W over 2 newtons, and on the other side you have W over 2 newtons. Now these red arrows, they are force vectors. And now it's important to realize that since we're dealing with limits, then we cannot say that the forces here equal W over 2. That would be wrong. That's not how you think about limits. In limits, you have to say that as your L approaches infinity, that's when your force vector F approaches W over 2. Not equals, but approaches. That's the thing with limits. You have to use arrows and you have to say approaches. Another way to think of it is like this. If in an ideal world L was infinity, then your force would be W over 2. It will never happen, But the closer L gets to infinity, meaning the longer and longer it becomes, the closer and closer this force gets to this value, W/2. So that's the logic behind limits. And so here I have a Python animation for you just to show this concept. This is your block, and these are your two wires. And so here you see that y equals 60 millimeters. So that's the vertical distance, but it's measured from here. You can see that you have 0 here, so I'm measuring it from here. But it doesn't matter. What matters is that if I run it now, then you see your L becomes bigger and bigger and bigger. You still have a triangle, but as your L increases all the time, you get closer and closer to this configuration where these wires become perpendicular to the block. They never reach that state, but they get closer and closer to that state, which means that your force vectors here and here, they become closer and closer to W/2 newtons. And so that's how you do it. Thank you very much. Welcome back. I have two small spheres here, and they are both positively charged. And that's why they repel each other with this force. According to the Newton's third law, the sphere A exerts a force, which is this one, to the sphere B, and sphere B exerts a force with the same magnitude but opposite in direction to sphere A. So this force is generated due to this positive electric charge. And this force can be calculated with this formula: F equals K times Q1 times Q2 over R squared. Let this Q1 be QA, which is the charge of this sphere, and let Q2 be QB, which is the charge of this sphere. This R here, that's the separation between these two spheres. And so this law here, it's called the Coulomb's law, and this K here, that's called the Coulomb's constant, and from physics its value is approximately 9 times 10 to the power of 9 Newton meter squared over Coulomb squared. Coulomb is a unit of charge. You have all the necessary dimensions here. Then the mass of this sphere, it's 0.2 grams, and MB is also 0.2 grams. And then we also assume that QA equals QB. So both of them have the same amount of charge, the same amount of coulombs. And you can see that the units here make sense, because if you take this part here, then the units of this part is Coulomb squared over meter squared. So if you multiply K by this, then in terms of units, M squared here will cancel out this one here, and then Coulomb squared here will get cancelled with this one, and you will only have newtons, which is the unit of force. And so since we assume that QA equals QB, we can just call it Q. So this formula becomes F equals K times Q squared over R squared. And so the question is, what is Q? What is the electric charge of these two spheres? Having all this information, your task is to calculate this Q. So try it out on your own first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now calculate the electric charge of the sphere A and B. Both charges are equal. And so let's focus on the sphere A. In order to find this charge, we first need to find this F. And so I'm gonna draw a free body diagram for this sphere A. Because it has mass, it also has force of gravity. Then sphere B applies this electric force to sphere A in this direction. And then here you have another force which is along this wire. So if I say that this point here, it's C, and this point here, it's D, then this force here would be FAC. Just to make it complete, I can also draw a free body diagram for the other sphere, sphere B. It has the same mass, so it has the same force of gravity. Then sphere A applies an electric force to sphere B in this direction, and then you have a force FBD here. Now notice that your masses are in grams. Since they are equal, I'm just gonna say that it's an M for both spheres. And I want to express it in kilograms, not in grams. So I will have 0.2 grams, and then I have 1 kilogram here, 1000 grams here. I cancel out the grams, and I will have 0.0002 kilograms. That means that the force of gravity for both spheres is 0.0002 times g. And then in the free body diagram, this is your positive x, and this is your positive y. Then also, this electric force is equal here and here due to the Newton's third law, action and reaction. You get a force because of these two charges, and then sphere A applies this force to sphere B, and then sphere B applies the same force but in the opposite direction to sphere A. And then you also see symmetry in terms of dimensions. You have 50 millimeters here. Here you have 150 millimeters. Here as well, 150 millimeters. Here the distance between them is 200 millimeters. Since their masses are the same, then because of this force, they will have the same angle here, let's call it alpha, and also here, alpha. So at the beginning, when they don't have charge, then they are like this, but since their masses are equal, once they start experiencing this electric force, because you had introduced a certain amount of charge into these spheres, since their masses are the same, and the wires here, they also have the same length, they will accelerate in the same way until they reach equilibrium. And that's because, as you can see here in the denominator, the bigger your R, the weaker your force. So at some point, this force will be cancelled out by the horizontal component of this FAC force. And the same thing here, at some point this F will be cancelled by the horizontal component of this FBD force. But since they have the same masses, they will have the same angles here, which means that these two forces are also equal. And so it doesn't really matter which sphere we analyze, but we can take this sphere A. But now, what we have to do, we have to figure out the direction of this FAC vector. Now, of course, we can do it with an angle. Let's say I'm going to calculate this angle theta here. However, we don't have to do it this way. In here, you can see that we have a right triangle, and we have the hypotenuse of this right triangle. And we also know this horizontal distance. The total distance between the spheres is 200 millimeters. Then here you have 50 millimeters. And since both of them have the same angle alpha here, and we have a right triangle here as well, that means that I have 75 millimeters here and 75 millimeters here. And so if you have 75 plus 50 plus 75, that will give you 200 millimeters. And now to calculate this h, we can use the Pythagoras theorem for that. H squared plus 75 squared equals 150 squared. And so we can say that H equals 150 squared minus 75 squared, and then all that square root. That will give me approximately 130 millimeters. So your H is 130 millimeters. And now, instead of having this angle theta here, I can draw a small right triangle here, and I can say that let this be 75, let this be 130, and let this be 150 millimeters. That's because this force vector goes along this wire. You have FAC here, and then you have FBD here. And so I can do the same thing here. I put 75 here, 130 here, and 150 here. And now we can use that when we use our equilibrium principle. So the sum of the forces in the x direction must be 0. And let's do it for this sphere A. So I will have minus F plus FAC. And now, instead of a cosine, we can just write 75 over 150. This ratio essentially is cosine theta. If this is your angle theta, then cosine theta would be 75 over 150. And then sine theta would be 130 over 150. And so this equation equals to 0. And then the sum of the forces in the y direction must also equal 0. And so I have FAC times 130 over 150, which essentially is sine theta. It will give me the vertical component of this force, and then minus and the force of gravity, which is this one here. And all that equals 0. Right away, I can calculate my FAC force from the second equation. So I'm going to put the force of gravity to the other side of the equation sign, and then it's going to be 150 over 130. And you already know what G is. G is always 9.81 meters per second squared. For as long as we are on the surface of the Earth, that's the value we need to use for G. And so if you calculate FAC, it will give you 0.00227 newtons. And then we take the first equation, and here you can see that your F equals this one. And I simply replace FAC with this number here, and I will get 0.00113 newtons. So that's the electric force that comes from this Coulomb's law. And so now I take this result here and I replace it with this force here. And here I have K times Q squared over R squared. Now since this K value has meters here, it means that this R should also be replaced with meters. So it will be 0.2 meters. So from here, I can write Q squared equals 0.00113 times R squared over K. And then what I do, I square root this entire thing. And so you know the K value, it's this one here. And then R is 0.2, so you will have 0.2 squared here. And if you calculate all that, then Q equals this number here. As you can see, it's a very small number. Here you have 10 to the power of minus 8. So it's a very small charge. So that's the positive charge that this sphere A has, and also that the sphere B has. And there you go. Thanks to the equilibrium principle, you found your Q. Thank you very much.